Okay, hi. So welcome to this recorded recitation. I hope you are enjoying your fall breaks or have enjoyed your fall breaks. This recitation was supposed to happen the week of fall break, but of course, since, we don't have classes, this is being recorded instead. We still want to keep on top of all of the content. So this recitation is purely for that, just to recap some of the stuff that we've already talked about. Thankfully, there's not much to cover, but let's just jump right into it. Actually, before that, a couple of announcements. If you are watching this during fall break, you have a midterm on Tuesday. I think it's Tuesday. Yes, it's Tuesday. Information about the exam is posted on Piazza regarding what content is on it. It's up to and including lecture 6T, as well as room assignments. If I recall correctly, it's section 1, which is the 8:30 section. Everyone will be in Meyerson B1. And then section 2, you're split across 2 rooms, one room being Fisher Bennett 419, the other one being Town 100, which is the room that you have lecture in. You should check Piazza to see which room you are in based off of your last name. Hopefully that's made clear on there. I forgot to mention if it was last name or not. Anyways, yeah, midterms coming up, study hard, material is there for you. Okay, enough rambling. You'll learn that I ramble a lot during these recitations, but let's get into it. There was only one slide today, so I decided to just write it up on the blackboard because I didn't feel like figuring out how the camera works with the projector screen. So yeah, it's just this. This is something that you saw in lecture on Tuesday, the 9th, and basically it's a bunch of equivalencies between facts about graphs. And this is incredibly good to be aware of. So let's read through it. For any n-vertex graph G, the following are equivalent. So G is a tree, meaning it's connected and acyclic. That is equivalent to saying that G is connected and has n-1 edges. Additionally, we can say that G is minimally connected, and so we'll touch on what this means in just a moment, but G is minimally connected. What this following are equivalent, what this means is that suppose I had a graph and I was told it's a tree, then I also know it's minimally connected. Or similarly, if I have a graph and I know it's connected and has n-1 edges, then I also know that it's a tree and it's minimally connected. So this is what I mean by the following are equivalent. If you have one of these things, you have everything else. So back to this minimally connected part. We've seen the word maximally here and there with connected components, for example. Minimally is sort of the opposite of this. So for a graph to be minimally connected, it means that the graph itself is connected. However, so that handles this this second part here of connected. Now we describe what minimally means. G is connected. However, for every single edge in our graph, if we were to remove the edge from the graph, G minus E, then that resulting graph is not connected. So that's what we mean by minimally connected, that no matter what edge we remove, if we were to remove it, we're left with a disconnected graph. So where's my chalk? I think one way of thinking about this is by saying that G is fragile. It is connected, but it's fragile. It will become disconnected very easily. Kind of opposite of that, but equivalent, is that G is maximally acyclic. So following the pattern from above, where G has this property, we say that G is maximally acyclic means that G is acyclic, the graph is acyclic. However, there's a whole bunch of notation here, but I'll explain it. However, for all pairs of vertices in our graph, if they're not adjacent to each other, meaning if they don't already have an edge between them, then adding that edge to the graph, the resulting graph, will contain a cycle. So the starting graph has no cycles, but if we were to add an edge to it, we would get a cycle. And remember, 4 is equivalent to 3, which is equivalent to 2, which is equivalent to 1. So if we have a graph that is a tree, we know it's maximally acyclic. And then number 5 is that any two vertices of G are connected by a unique path. So this is a really good property about trees, I suppose, because you just look at any two vertices and you know that there's only one path that connects the two of them, and it's unique. So like I said, all of these are good to know. If you see a problem and you know that and in the problem they say, consider a graph that is minimally connected, then you also know it's a tree. You also know it has n-1 edges, all of that good stuff. Let me quickly draw out an example to show all of these properties, but I'm going to erase this because I don't have room. So let's do it. Okay, so here I've drawn a graph that has 18 vertices, and we'll check all of the things from before to see if they are equivalent. So first was that, the thing is a tree. So in this case, I'm just telling you that this is a tree. You can quickly verify it. It's connected and acyclic, so we're chilling. I believe the next one is that G is connected and has n-1 edges. We already know about the connected part. Let's count the amount of edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So we do have 17 edges. Okay, the next fact was about the tree being minimally connected, which means if I were to remove any edge, then the graph becomes disconnected. So you can try it. Remove any edge you want, and now our graph is disconnected. Maybe we just got lucky. Let's try a different edge. Maybe this one. But you can see, once again, it's disconnected. We have an isolated vertex there. So indeed, it is minimally connected. The next thing was about the graph being maximally acyclic, meaning if I were to add any edge which doesn't already exist, then we would get a cycle. So, choose any two vertices and add an edge. Let's do this vertex and that vertex. And indeed, I have a cycle going from here, there, 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 and back. So that creates a cycle. Let's try one more. Maybe just these two. And again, we have a cycle. And no matter what edge you add, it'll create a cycle. And the last thing was about unique paths between vertices. So suppose I have a vertex, or a pair of vertices U, V. I can find a unique path between them, and it's this one. That's the only path between U and V. No other paths exist. So all of the equivalences hold, so it's good that that's factual. Cool. Okay, so that handles lecture review. Let's do a couple of problems. Okay, so here's our first question. Let T be a tree with maximum degree delta. Prove by contradiction that T has at least delta leaves. This is one of the most important problems that we cover in recitation, purely because we have a ton of solutions for this problem. You can solve this in any way you can think of. If we were in person, what I would do is I would ask the students, what proof technique would you solve? And what proof technique would you use to solve it? Someone would say direct proof, someone would say induction, someone else would say handshaking lemma. And at the end, I'm like, well, you're all right, because all of those in fact work. So I highly encourage eventually seeing all of the solutions for this problem because it helps with different proof techniques. But in this case, we're asked to prove it by contradiction. So before we even get into contradiction, let's just verify that this may seem correct. So I'll draw a tree. So this is my tree, and there's a vertex that must have the maximum degree. In this case, it's this central vertex. So big delta in this graph is 4. All other vertices have degree 4 or less. And then I want to see if there are at least 4 leaves. So remember, leaves have degree 1. So if I were to count these vertices, it would be 1, 2, 3, 4, 5, 6. So I have 6 of these. And indeed, I do have at least delta leaves. So it seems to work out with this case, which is good. So let's try solving it. So in a proof by contradiction, we should start by explaining what our contradiction statement is. So we'll write our proof. We will assume for a contradiction what are we assuming? Well, we're asked to prove that T has at least delta leaves, so we will take the negation of that. At least delta leaves can be considered greater than or equal to delta leaves. So if we were to take the negation of that, it would be assume for a contradiction that T has less than delta leaves. Okay, so we have our contradiction statement, we have a tree to work with, let's get to work. So what do we know about this tree? It has maximum degree delta. That is just the one fact we know about the tree. What other stuff do we know about trees? It has, n minus 1 edges. If it has n vertices, it's minimally connected, it's maximally acyclic, all of those things from before. And while we know so many facts about trees, we should start to be thinking, which one of these things actually help us? Does the fact that a tree is maximally acyclic, is that going to help us find the amount of leaves we have? Probably not. So this is a skill that you'll have to gain as you practice of, knowing so much information but filtering out things that seem unnecessary for the problem. Okay, so let's focus in on this vertex with maximum degree delta. That's what it means for the tree to have maximum degree delta. There exists some vertex with degree delta. So let's write this down. There exists a vertex such that the degree of V is equal to delta. And bear with me, when it comes to graph theory, I write my V's as a little curly, just to differentiate them from U's, because those are the letters we normally use. Okay, so let's consider what delta could be. If delta is equal to 0, then V must be a single isolated vertex, because, it has degree 0. And in fact, this will be the only vertex in our graph because we have that the graph is a tree. So in this case, we consider this to be a leaf. And we have that 1 is not less than 0. So that would contradict our assumption here. So this is a contradiction. Okay, what if delta equals 1? Well then our vertex V has degree 1, so it's connected to something else. But how can we extend this tree? We can't, actually, because if we were to add any edge to this vertex here, sorry, this one is V. If we were to add any such edge, then this has degree 2, but we said the maximum degree is 1. So we can't add anything to this graph. So this is the only graph that's a tree with maximum degree 1. And here we have 2 leaves. And 2 is not less than 1, so this is also a contradiction. Okay, so far so good. Let's try delta equals 2. So we have our vertex V. It has its neighbors. And now we think, okay, how else could this graph look? So since the maximum degree is 2, that means all vertices can have degree 2 or less. It's not just V that has degree 2. So maybe this one has another neighbor, and maybe this one does too, and this one might have one too, and so on. And we can see that, you know, it's not just one graph this time, it's multiple graphs, like an infinite amount of graphs. So we can't really continue with this casework. It's going to be pretty bad pretty soon. But now we've already handled the cases 0 and 1, so we will separately handle the case where delta is greater than or equal to 2. And hopefully the remainder of the proof will prove all of these cases. It's just these edge cases, when delta is small, are kind of annoying, so just handle them first. Okay, so delta is greater than or equal to 2. Again, we have this vertex V that has like all of these neighbors. So let's define S to be the set of vertices U such that UV is an edge in our graph. So S is just going to be the set of neighbors of V. This is the set of neighbors of V. And this is just for convenience because now we know that the cardinality of S is equal to delta. By definition, because we said V has the maximum degree. Let's say I started at V and I began to walk along my edges and like try to construct a path of sorts. If I start from V and perhaps go to A, and you know A is connected to other things, and so on, eventually I'll come to an end of my path. Let's just say I keep on going until I can't go any further. Where am I going to end? Well, I'm going to end at a leaf. Why? Well, let's prove it. So my claim So what I'm really trying to say is if I were to take any vertex in the neighbor set of V, then there's going to be a unique path starting from V that goes to the neighbor, and I keep on going until I finally reach a leaf L, such that each path ends in a different leaf. Meaning, when I look at all of the paths from V to, U, which is in the neighbor, to a leaf, V to a different neighbor to a leaf, V to a different neighbor to a leaf, all of those ending leaves are going to be different. I won't write out the proof because there's not too much space and someone's about to kick me out of the room, so I will argue why. Well, first, why does this end in a leaf? Suppose not. Then, where does it end? If it's not a leaf, it's going to be a vertex with more than degree 1, so I can enter the vertex through one edge and leave it through a different edge, and I'll basically end up cycling all around, and we can't have that because trees don't have a cycle. And additionally, they're all different leaves, because if I had two different paths that ended in the same leaf, then I would have a cycle, right? If I go V to U, that ends in a leaf, and V to a different neighbor that ends in the same leaf, then I have a cycle. So that can't happen either. So this claim holds true.
Okay, so sorry for the abrupt change in scenery, but I was kicked out of that room and then I had to travel a bit, so we still continue with the recitation. So we're actually almost done with this question. Let me just take you through what we've done thus far. So we had our contradiction statement. We showed that it was false for delta equals 0, delta equals 1, or not false, but rather a contradiction erupted. Now we consider the case where delta is greater than or equal to 2. We've named such a vertex in our graph T. We called it V, such that the degree of V is delta. We defined S to be the set of neighbors of V, and the cardinality of S is equal to delta. Next, I claim that for all neighbors of V, there's a unique path from V to that neighbor that ends in a leaf. And when I look at all of the paths, they all end in different leaves. And I sort of verbally explained to you why that was the case, and the argument was that it has to end in a different leaf, otherwise we have a cycle. So from here, the proof is actually really quick to complete. So, I mean, one way of concluding this is that, therefore, like, each element U and S contributes its own leaf to the tree, and the word contributes is used very loosely here, because the leaves already exist, so to speak, but since each path that starts from V goes to U ends in its own leaf, this would tell us that we have delta leaves, but we assumed less than delta, so that would be a contradiction. Alternatively, I think we can kind of avoid going about this claim and instead just prove a weaker claim. And a weaker claim would be like, for all U in S, there exists a path, or suppose like a unique path, since it's a tree, that goes from V to U that ends in a leaf. So if we were to prove that, there exists such a path, we're going to disregard the fact about, them ending in a different leaf, and that will be proven later. Then we have delta paths from V that end in a leaf. But now the thing is, we assumed that there are less than delta leaves. So by assumption, we have less than delta leaves in T. And let's say that there are A. Let there be A leaves, just so we have a variable to work with. And now we'll handle this part of them like being different leaves by a pigeonhole argument. So if we let the paths be pigeons, and we let the leaves be holes, then by PHP, there exists a leaf that has, let's write this out, that has ceiling of some quantity, amount of paths, but really the paths end in leaves. So it's that that has some amount of paths that end in that leaf. Okay, so now we just want to fill in this fraction. So the numerator would be the pigeons. We have delta paths, and the denominator is the amount of leaves. So this is going to be A leaves. We know from assumption that A is less than delta, or equivalently, A is less than or equal to delta minus 1. So this fraction of delta over A is equal to the ceiling of delta over delta minus 1. We can rewrite this as 1 plus 1 over delta minus 1, and this is equal to 2. So this is telling us that there are two paths that start from V and end in the same leaf. But that would imply that there exists a cycle. And that is a contradiction. So really, like, this part up here and the second part here are equivalent. It's just the top one does a stronger claim, and the second one is a little bit weaker, but we reconcile the strength missing by this pigeonhole principle argument. Both proofs completely valid, just two different ways of doing contradiction here. So there you go. That is this problem done by contradiction. It will probably appear again maybe next week. Like I said, there's a lot of different ways to solve this problem, so you should try some of them out on your own. Let's move on to the next and last question. So this is saying prove that G or the complement of G is connected, and note that the complement of a graph is basically this graph on the same vertex set such that edges only appear if they do not appear in the original graph. So I will try to explain this with a drawing. So let's suppose we have this graph on 4 vertices, and I don't know how to do this correctly. Maybe something like this, right? Now each graph has a unique complement, meaning that there's only one of them, so there's always a correct complement, and it's defined on the same vertex set. So the way we find the edges of a complement graph is we look at the original graph and we see which edges are not present. Or equivalently, if I were to look at every single pair of vertices, if there exists an edge in G between them, then I will not draw an edge between them in G complement. However, if there does not exist an edge between them in G, then that edge will appear in G complement. So, for example, this edge is missing in G, and that edge is missing in G as well. Otherwise, all of the edges are present in G, so they must not be included in G complement. So now we know how to compute the complement of the graph. We're asked to prove that G or G complement is connected. In this example drawing, G is connected, G complement is not connected, but this verifies the potential of this claim being true because, we have one of these conditions being filled, in this case G being connected. The complement of G is not, but it doesn't matter. We just need one of these to be true. Okay, well, how are we going to do this? Well, the first thing to note is that we're proving this for all graphs. Every single graph, either G or its complement, is connected. So when we think of for all, sometimes a natural thought is induction. However, I highly advise going for induction immediately with graph problems. That's a discussion for another time of why induction isn't always super friendly with graph theory, but you can imagine it becomes really complicated. So how else could we do this? What if we just consider an arbitrary graph G, and if we were to show that this graph is either connected or its complement is connected, then we're good, because G is just completely arbitrary. So let's let G be an arbitrary graph. So we have some graph that, someone drew on a board, perhaps, and, we need to argue that this is true. Well, let's say that I just drew a graph on a board for you. If it's connected, then we're good. We don't have to deal with anything. So basically, we can consider 2 cases. Case 1, the graph G is connected. And case 2 will be G is not connected. Right, this is the, just based off of definition of connected in graphs, either a graph is connected or disconnected. In this first case, then we're done. We have shown that G or its complement is connected because, well, we know it's connected. We don't really care if its complement is connected or not because we found one condition to be true. The issue where it comes where G is not connected, because now we actually have to take a look at its complement. But this might be a little bit challenging, right? Because we don't see the graph. We don't have something to draw out like I did over here. This was a specific example. Again, G is just arbitrary right now. So we have to consider G complement, but in sort of an abstract mindset. So our goal here is to prove that G complement is connected. That's what we need in order for the proof to be valid, for this claim to be true. We must show that G complement is connected. How do we show that something is connected? We can show this, we do this by showing that every pair of vertices has a path between them. If we can show that, then by definition, our graph is connected. So again, we have to show this for every pair of vertices, all pairs of vertices. We can handle this by, again, considering an arbitrary, in this case, pair of vertices. If we show it for an arbitrary pair of vertices, then it holds for all of these vertices. So let's consider an arbitrary UV, which are two vertices in our vertex set, and we will show there exists a path between them. Okay, well, again, we don't have G complement with us. We've only considered like an arbitrary G, and like, again, that's not completely fleshed out for us. We don't really know what it looks like, because whatever we prove must work for all graphs. So we just sort of have the definition of G complement to work with, meaning that an edge appears in G complement if it doesn't appear in G. Interesting. An edge appears in G complement if it doesn't appear in G. Why don't we write that down? Let's say that UV will have an edge in G complement if the edge UV is not in G. Okay, well then this is kind of naturally admitting some casework. So let's consider like case A, which would be that UV is not an edge in G. Well, this is, if that's the case, then we just use the conclusion or the observation we made from above. So there's an edge UV in G, which means that there is a path between U and V in G complement. Good. So again, before we proceed, just to recap, we're considering a pair of vertices. We want to show that there's always a path between them in G complement. And so we can just case like either they have an edge in G or they don't. In this case, we handled the case where they don't have an edge in G. So the last thing we have to consider is case B, is that the edge UV is an edge in G. And of course, we want to show that there's a path between them in G complement. Well, what do we know about G? We know that G is disconnected. That is the case we're under. So G has multiple connected components, not just one. If it was one, it would be a connected graph. So G has greater than or equal to 2 connected components. I'm just going to abbreviate it CCs because that would take forever to write out. Okay, so G has multiple connected components. Let's sort of like draw it out. You know, I'm just drawing these circles, and there could be many of these circles, but each one of these is its own connected component. But if UV is an edge in G, then we know that if U is in like some connected component, V must also be in the same connected component. So U and V are in the same connected component. Right? They can't be in different ones because there's an edge between them. They're connected to each other, right? But why is this notion of multiple connected components so important? Well, if I were to look at some other connected component that doesn't have U and V, and there's some other vertex A, what do I know about U and V in their relationship to A? Well, since they're in separate connected components, U cannot be connected to A, V cannot be connected to A. So if I were to look at the relationship between U and A, that dotted edge that I just drew does not exist. And similarly, V to A doesn't exist. So these kind of edges, I'm really bad with this software, but whatever. These edges do not exist in G, right? These different connected components. However, if they do not exist in G, I'll just write these out. This is UA and VA. Those edges do not exist in G. However, that must mean UA and VA must appear in G complement by definition, since they don't appear in G. Well, then life becomes really easy because we just go from U to A to V and we have a path. And this, in fact, is the end of the proof, which is kind of crazy. I just want to briefly walk you through everything we just did, just to make sure it makes sense. So we started with our graph. If it's connected, we're good, we're done. We're absolutely done. If it's not connected, then we have to show that its complement is connected. To show connectivity, we will consider every pair of vertices in the graph and show that there's a path between them. This is the definition. This is definition of connected. Remember, proofs are all just using definitions. So that's how I came up with that idea. Well, again, since I'm showing it for every pair, I'll consider an arbitrary pair of vertices and show that there exists a path. I can break this down into cases. If there's not an edge between them in G, then that edge must exist in G complement, and thus there's a path between them in G complement. The other case is that there is an edge in G, and before I explain the rest of this proof, again, we're showing this for every pair of vertices U and V in our graph, and no matter what pair I choose, they will always fall into one of these two. So I'm being very exhaustive with my casework, and in both cases I'm showing there exists a path. Okay, so back to this. If there is an edge in G, then we know that G is disconnected because, we're under this case where G is not connected. So we have multiple connected components. We can find a connected component which has a different vertex, but first we recognize that U and V are in the same connected component. So we consider a vertex outside of that connected component. We recognize that the edges U to A and V to A must not exist in our graph G. So since they do not exist in G, they must appear in G complement. We have a path between them. So always, no matter which two vertices we're looking at, there will always exist a path between them in G complement. Therefore, G complement is connected. As I mentioned at the start of this recitation, I tend to ramble a lot, but this is purely so you can see every single thing that I'm thinking about, and when it comes your time to write out these kind of proofs, you kind of get the feeling of what things you should be thinking about. So yeah, that's this problem. Very helpful and honestly a very cool fact. A good exercise or something to think about is that is it always exactly one of G or G complement is connected? Or is it ever possible to have neither of them connected or both of them connected? You should be able to very easily argue why neither of them being connected is not possible, but figuring out whether or not exactly one is connected, that's something I'll leave to you to do. It's pretty fun. But yeah, that is the end of this recitation. Again, if you're watching this during fall break, thank you for spending your time with me. Good luck on the exam. And if you already had the exam, thank you for watching. That's all I could ask for. Anyways, have a good rest of your day. And yeah, let's end it here.